Hello there, and welcome. I am the sleepy astronaut. I'm so glad you found your way here. Perhaps it's been a long day for you, and you are seeking rest amongst the stars, or maybe you just love learning calm, gentle facts about space and science. Either way, tonight's journey is for you. This evening, we will be exploring one of your local solar system's most incredible phenomenon, the Oort Cloud. Whenever I float back to Earth to pick up new astronauts, passing through the Oort Cloud is my favorite welcome. Picture an unimaginably vast, pitch-black spherical shell of trillions of ancient, glowing ice mountains, floating in a silent, freezing void far beyond Pluto. Stretching a quarter of the way to the next star system, it acts as a primordial cocoon, holding the leftover building blocks of the solar system's birth. If you enjoy these calm journeys through space, I invite you to subscribe or leave a thought below. It helps other astronauts find their way here. But for now, your day on Earth has come to an end, and your journey through the stars has begun. You don't need to do anything, just relax and let your body sink. Let your eyes grow heavy, and allow your mind to drift into space. Let's take off. To truly understand this colossal expanse, we must step outside the familiar sunlit inner planets, where humanity carved its civilization. We leave behind the warm terrestrial cradle of Earth, the rust-red deserts of Mars, and the roaring gas giants of Jupiter and Saturn, pressing ever outward into the deep, frozen twilight. Beyond the icy realm of Neptune and past the distant, crowded rocks of the Kuiper Belt lies a true frontier, a zone where the sun is no longer a blazing golden disk warming the planets, but merely a bright, cold star among millions in the ink-black velvet of the Milky Way. Here, in this endless expanse of absolute zero, rests the Oort Cloud, a majestic and mysterious reservoir that wraps around our entire solar system like an enormous, invisible bubble. Unlike the flat, disk-like plane where the planets orbit in neat, orderly tracks around the equator of the Sun, the Oort Cloud is a towering, three-dimensional sphere. It envelops our celestial neighborhood from every conceivable angle, stretching upward, downward, and outward in all directions. Within this titanic spherical shell dwell trillions of independent icy bodies, ranging from massive, mountain-sized comets down to smaller shards of frozen gases and primordial dust. These objects are not active or glowing with the fiery passion of active comets near the Sun. Instead, they are frozen solid, trapped in a deep, cryogenic slumber that has lasted for more than 4.5 billion years. They are pristine time capsules, preserved in the ultra-cold vacuum of deep space, holding chemical signatures and material remnants from the violent, chaotic birth of our planetary system. The sheer scale of this region defies human intuition and stretches the limits of our imagination. When astronomers talk about distances in our solar system, we usually rely on astronomical units, where 1 astronomical unit is the average distance from the Earth to the Sun. Pluto sits roughly 40 astronomical units away, a distance that takes light over 5 hours to cross. Yet, the inner boundary of the Oort Cloud begins thousands of astronomical units away from the Sun, and its outer limits stretch outward for a staggering distance of up to 100,000 astronomical units, or nearly 2 light years. To put that in perspective, the Oort Cloud reaches nearly halfway to Alpha Centauri, the nearest neighboring star system. If you were to draw a map of the solar system, where the distance from the Earth to the Sun was scaled down to the size of a single meter, The Oort Cloud would extend outward for miles, engulfing entire towns in its invisible frozen embrace. For the longest time, humanity remained entirely oblivious to this colossal outer realm, because the objects within it are far too small, dark, and distant to be seen even by our most powerful modern telescopes. The existence of the Oort Cloud was not discovered through direct observation, but rather through brilliant scientific deduction and the stubborn mystery of long-period comets. For centuries, astronomers puzzled over comets that appeared out of nowhere from deep space, plunging inward toward the inner solar system on wildly elliptical orbits that took thousands or even millions of years to complete. These were not regular visitors like Halley's Comet. They were strange, unpredictable apparitions that came tumbling in from random directions across the sky, slicing through the plane of the planets at every imaginable angle and inclination. The breakthrough came in 1950, when the Dutch astronomer Jan Oort analyzed the orbits of these long-period comets and noticed a profound and startling pattern. When he calculated the paths of these icy wanderers backward to where they originated before falling toward the Sun, he discovered something remarkable. Their aphelia, the furthest points of their orbits where they spent the vast majority of their existence, clustered heavily at a tremendous distance of roughly 50,000 astronomical units. No matter what direction in the sky these comets arrived from, their distant turning points pointed to a common, massive reservoir that surrounded the entire Sun in a spherical distribution. Oort realized that these comets were not interstellar travelers coming from random points in the galaxy, but rather native residents of our own solar system that had been nudged out of a distant, hidden cloud by passing stars or galactic tides. This brilliant realization transformed our understanding of the solar system's true boundaries. Jan Oort demonstrated that the Sun's gravitational dominion does not end at the orbit of the furthest planet, or even at the edge of the Kuiper Belt. Instead, the Sun maintains a fragile, ghostly grip on trillions of icy objects, stretching outward across a vast abyss of interstellar space. These objects move at a glacial pace in their massive, lazy orbits, taking millions of years to complete a single revolution around the distant, dim Sun. They drift in absolute silence, separated from one another by millions of miles of empty vacuum, yet bound together by a shared history and the faint, enduring gravity of our star. As we gaze out into this profound darkness, we begin to realize that our solar system is not a small, isolated island, but a sprawling, majestic empire that reaches far beyond anything our eyes can see. The Oort Cloud stands as a monument to deep time, a frozen archive holding the secrets of how our world came to be. It is the outer edge of our cosmic home, a vast and silent frontier where the Sun's light fades into the eternal night, and where the true story of our solar system's birth is written in ice and stone. To truly grasp the magnitude of the Oort Cloud, we must look beyond its sheer physical boundaries and examine the staggering population that inhabits it. Scientists estimate that this colossal spherical reservoir contains not millions or even billions, but trillions of independent, icy bodies drifting in the dark. If you were to gather every single one of these frozen worlds and combine their mass, it would equal anywhere from a few to perhaps several times the total mass of planet Earth. Yet this immense amount of material is not concentrated into a single planet or even a dense asteroid belt. It is diluted across a volume of space so incomprehensibly vast that individual objects are separated by millions of miles of absolute nothingness. They are solitary wanderers, locked in a perpetual, silent orbit around a sun that appears to them as nothing more than a brilliantly sharp star in a sea of eternal night. Modern planetary science divides this colossal structure into two distinct regions, each with its own unique architecture and dynamical behavior. The inner portion, often referred to as the Hills Cloud, has a more disc-like or toroidal shape, resembling a thick, bloated donut that sits closer to the plane of the planets, though still far beyond the Kuiper belt. The Hills Cloud starts roughly 2,000 astronomical units from the Sun and extends outward to about 20,000 astronomical units. Because it is closer to the Sun, the gravitational grip here is slightly stronger, keeping the objects somewhat more densely packed and bound to the plane of the solar system. Beyond the Hills Cloud lies the outer Oort Cloud, a true spherical shell that billows outward in all directions, completely encasing the inner planets, the gas giants, and the Kuiper belt in a three-dimensional bubble that stretches all the way to the very threshold of interstellar space. The most fascinating and counterintuitive truth about the Oort Cloud is that these objects were not actually born where they reside today. The extreme outer edges of the solar system are far too cold, sparse, and devoid of dense material to have ever coalesced into solid bodies on their own. Instead, the icy mountains of the Oort Cloud are refugees from the violent, chaotic construction site of the inner solar system, exiled to the freezing periphery by the gravitational fury of the giant planets during the infancy of our cosmic neighborhood. 4.5 billion years ago, the young solar system looked nothing like the orderly clockwork we see today. It was a chaotic, turbulent disk of gas, dust, and countless building blocks known as planetesimals, all swirling around a newly ignited sun. In the inner and middle regions, massive protoplanets were rapidly forming, sweeping up debris and carving out their domains. Among them, the gas giants, Jupiter, Saturn, Uranus, and Neptune, grew with terrifying speed, accumulating immense gravitational fields that allowed them to dominate the surrounding disk. As these colossal planets migrated and shifted their orbits through gravitational interactions with the primordial disk, they acted as cosmic gravitational engines, sweeping up smaller icy and rocky bodies and flinging them violently across space in a massive game of gravitational billiards. Most of the planetesimals that got too close to Jupiter and Saturn were ejected entirely out of the solar system, banished into interstellar space to wander the galaxy as lonely orphans. But objects that interacted with the outer ice giants, Uranus and Neptune, experienced a different fate. Their trajectories were deflected into wide, highly elliptical orbits that sent them soaring far out into the deep freezing margins of the solar system. When these flying mountains reached the aphelion of their newly altered paths, thousands of astronomical units away from the Sun, their outward momentum slowed to a crawl. At this extreme distance, the Sun's gravity was weak, but it was just barely strong enough to prevent them from escaping completely. Yet simply being flung outward was not enough to create the spherical Oort Cloud we see today. If left alone, those scattered objects would have continued on flat, elongated orbits, plunging back inward toward the Sun every few million years like a swarm of bees passing through a pinhole. What transformed this flat spray of ejected debris into a towering, three-dimensional spherical shell was the gentle, patient touch of the wider galaxy. As the solar system orbits the center of the Milky Way, it passes through subtle gravitational gradients known as galactic tides, and occasionally drifts near passing stars or dense, giant molecular clouds. Over hundreds of millions of years, the collective gravitational tug of passing stars and the immense tidal forces of the Milky Way galaxy itself acted upon those distant, lazy ice bodies. These external forces subtly altered their orbital planes, tilting them, twisting them, and randomizing their trajectories. An object that was originally flung out on a neat, flat trajectory was gradually nudged and torqued into a completely different angle. Multiply this process across trillions of objects over billions of years, and the result is a majestic, spherically symmetric cloud that wraps around our Sun from every conceivable direction. In this way, the Oort Cloud became a museum of planetary history, preserving the scattered debris of our system's birth in a cryogenic vault. The ice mountains that drift there today are the literal ghosts of the worlds that might have been, cast out into the dark, so that the inner planets could find stability and allow life to take root. As we study this grand reservoir, we are looking at the distant echoes of our own origins, written across the deepest canvas of space. To truly appreciate the architecture of the Oort Cloud, we must look closer at how this colossal region is internally organized. It is not a uniform, haphazard fog of ice, scattered evenly across the void. Rather, it is divided into two distinct, highly specialized zones that behave under entirely different physical rules. These two regions, the inner Hills cloud and the massive outer spherical shell, represent a profound transition in how gravity shapes matter at the absolute margins of a star's influence. The inner region, known to astronomers as the Hills cloud, acts as a heavy, bloated donut or a thick disk that sits much closer to the plane of the planets than its outer counterpart. While the Kuiper belt ends around 50 astronomical units from the Sun, the Hills cloud begins roughly 2,000 astronomical units away and stretches outward to about 20,000 units. In this intermediate zone, the Sun's gravitational grip is still strong enough to maintain a memory of the original flattened disk from which the solar system formed. Because it sits closer to the solar system's gravitational equator, the objects here are more tightly bound and heavily populated, containing a staggering density of frozen bodies compared to the vast emptiness beyond them. The objects in the Hills cloud are caught in a delicate tug-of-war between the Sun and the broader galactic environment. Because they are closer in, they do not experience the wild, randomizing kicks from passing stars as frequently as their outer neighbors. Instead, they move in slower, more orderly paths that still roughly align with the general rotation of the planetary disk. Yet, over long spans of time, gravitational perturbations from passing stars and the immense disk of our galaxy slowly grind away at this inner structure, acting like a cosmic slow cooker that gradually nudges objects out of the Hills cloud and feeds them up into the outer shell. Beyond the 20,000 unit mark, the character of the Oort cloud changes completely, bleeding outward into the outer Oort cloud. Here, the Sun's gravity has weakened to a faint, ghostly whisper, barely strong enough to hold onto the icy wanderers that drift through the dark. This outer shell billows outward in all directions, forming a true three-dimensional sphere that completely envelops our planetary system like an enormous, invisible soap bubble stretching all the way out to 100,000 astronomical units. In this realm, the flat, orderly geometry of the inner solar system is entirely erased. Objects here move on wildly randomized orbits, tilted at every conceivable angle, drifting through space in absolute isolation. The outer shell is a fragile and dynamic place, constantly being reshaped by the restless galaxy around us. Because these objects are so far from the Sun, they are exceptionally sensitive to external forces. Whenever a passing star drifts within a light year of our solar system, or when the immense tidal forces of the Milky Way galaxy pull unevenly across the cloud, it is the outer shell that feels the blow first. A single stellar flyby can send a shudder through the outer Oort Cloud, dislodging millions of icy bodies from their stable paths and sending them plunging inward toward the Sun as long-period comets, while leaving the denser inner Hills cloud relatively undisturbed. This structural division creates a natural conveyor belt for cometary visitors. When comets are knocked loose from the outer shell, they make their long, multi-million-year journey inward. But many of them are eventually recaptured or randomized into the Hills cloud, replenishing the inner reservoir. Together, the disk-like inner Hills cloud and the spherical outer shell form a magnificent, interconnected engine of ice and gravity, guarding the perimeter of our solar system and preserving the ancient history of our cosmic birth in the deep, silent cold. While the trillions of icy bodies resting within the Oort cloud spend billions of years locked in a deep, frozen slumber, that eternal quiet is occasionally shattered by the dynamic forces of the galaxy. Every so often, a quiet catastrophe occurs at the edge of the solar system. A passing star drifts close enough to whisper its gravitational influence through the outer shell, or the massive tidal forces of the Milky Way's spiral arms exert an uneven pull across the sprawling cloud. For the vast majority of Oort cloud objects, these subtle forces go unnoticed. But for a tiny fraction of them, these gentle nudges are enough to alter their delicate orbital balance, tipping them off the edge of stability and sending them on a catastrophic, multi-millennial plunge toward the inner solar system. This is the birth of a long-period comet, one of the most majestic and unpredictable visitors to grace our cosmic neighborhood. To understand the magnitude of this journey, we must look at the nature of the gravitational nudge itself. In the pristine void of the outer Oort cloud, objects move with agonizing slowness, orbiting the distant Sun at speeds measured in mere meters per second. Their orbital paths are immense, stretching out over millions of years for a single revolution. When a galactic tide or a passing stellar companion tugs on one of these slumbering ice mountains, it shifts the shape of its orbit from a wide, lazy arc into a radically elongated ellipse. The object is no longer content to drift safely in the dark. Its new trajectory is aimed directly at the heart of the solar system, millions of miles away. Once pushed from its stable home, the comet begins an unimaginable journey inward. At the start of its descent, located tens of thousands of astronomical units from the Sun, the fall is almost imperceptible. The comet creeps forward through the absolute blackness of deep space, taking hundreds or even thousands of years just to cross the outer threshold of the solar system. As it descends deeper down the invisible gravitational well carved by our star, something remarkable happens, governed by the unyielding laws of orbital mechanics. Month by month, century by century, the comet begins to pick up speed. The vast emptiness of space starts to blur, and the distant Sun slowly grows from a faint, pinprick star into a sharp, blinding beacon of light. After thousands of years of continuous falling, the comet crosses the distant boundary of the Kuiper belt, slicing past the orbit of Neptune and plunging through the realm of the gas giants. By this point, its velocity has surged from a crawl to tens of kilometers per second. It streaks through the planetary plane like a celestial bullet, slicing across the orbits of Saturn, Jupiter, and Mars at a terrifying angle. Unlike short-period comets originating from the Kuiper belt, which follow tidy, predictable paths aligned with the general disk of the planets, Oort Cloud comets arrive from every random inclination imaginable. They plunge downward from high northern latitudes, streak upward from the southern polar regions, or slice diagonally across the solar system's equator, defying all expectations of order. As the comet races closer and closer to the Sun, the environment shifts dramatically from deep freeze dormancy to intense, destructive solar energy. For billions of years, this primordial mountain of ice and dust has remained untouched by warmth, preserving frozen volatile gases like carbon monoxide, carbon dioxide, methane, and ammonia deep within its crust. But as the comet sweeps inside the orbit of Mars and approaches the inner terrestrial realm, the relentless onslaught of solar radiation begins to take its toll. The surface temperature climbs rapidly, turning the ancient ice directly into gas through a process known as sublimation. Jets of pressurized gas and boiling dust erupt violently from weak spots in the comet's dark, carbon-coated crust, punching geysers of vapor into the vacuum of space. This escaping gas and dust billows out around the solid nucleus, forming a glowing, ghostly atmosphere known as a coma that can expand to a size larger than the planet Jupiter. At the same time, the solar wind and the pressure of sunlight sweep this liberated material backward, sculpting it into two magnificent tails that stretch for millions of miles across the night sky. One is a straight, brilliant blue ion tail, composed of electrically charged gas molecules pointing directly away from the Sun, while the other is a broad, curving dust tail that traces the comet's orbital path in a glittering arc of reflected starlight. For humanity, these rare visitors offer an unprecedented scientific gift. Because long-period comets spend almost their entire existence sequestered away in the ultra-cold deep freeze of the Oort Cloud, they have remained chemically unaltered since the formation of the solar system 4.5 billion years ago. They are pristine, unadulterated time capsules from the protoplanetary disk, holding the original organic molecules and water ice that helped seed the inner planets. When a naked-eye comet lights up our evening sky, we are not just witnessing a random piece of space debris. We are looking at an ancient messenger from the absolute edge of our star's dominion, delivering the primordial history of our cosmic birth directly to our doorstep, before it whips around the Sun and begins its multi-million-year journey back out into the dark. While the vastness of the Oort Cloud offers an illusion of eternal stability, it is actually a dynamic and constantly harassed frontier, buffeted by the immense forces of the wider galaxy. The Sun's gravity alone is not enough to maintain absolute order across a realm that stretches nearly halfway to the nearest star. Instead, the Oort Cloud exists in a delicate equilibrium, constantly reshaped and disturbed by two primary external sculptors: the subtle, unrelenting pull of galactic tides and the occasional violent disruption of passing stars. To understand why comets continually break free from their cryogenic slumber, we must look beyond our solar system and examine the macro environment of the Milky Way itself. The first and most pervasive force acting upon the Oort Cloud is the gravitational tide of our galaxy. The Milky Way is a majestic spiral containing hundreds of billions of stars, vast clouds of gas, and dense reservoirs of dark matter, all rotating around a galactic center. Because the Oort Cloud is so extraordinarily massive, spanning trillions of miles, it does not experience the gravity of the galaxy uniformly. The side of the Oort Cloud closest to the center of the galaxy, and the side facing the galactic disk, experiences a slightly stronger gravitational pull than the opposite sides. This differential gravitational force creates what astronomers call a galactic tide, a silent, invisible stretching mechanism that constantly pulls and torques the outer edges of the cloud. This galactic tide exerts a powerful vertical component, pulling rhythmically up and down on the spherical shell of the Oort Cloud as the solar system bobs through the midplane of the Milky Way galaxy during its massive 200 million year galactic orbit. This relentless tidal flexing acts like a slow-motion cosmic heartbeat, subtly warping the orbits of distant icy bodies. Over hundreds of millions of years, the cumulative effect of the galactic tide gradually grinds away at the circular paths of Oort Cloud objects, twisting their trajectories, tilting their inclination angles, and steadily driving them inward or outward. Without the gentle, persistent persuasion of the galactic tide, far fewer comets would ever find their way into the inner solar system, leaving our cosmic neighborhood vastly quieter than it actually is. Yet while the galactic tide provides a steady baseline of disruption, the truly dramatic events are driven by passing stars. Our sun is not stationary in the galaxy. It is a traveler, drifting through the local interstellar neighborhood alongside thousands of other stars. Every few million years, another star wanders relatively close to our solar system. While close in interstellar terms still means a distance of several light years, far too distant to pose any immediate threat to the inner planets or disrupt the orbit of Earth. It is close enough to brush against the outer fringes of the Oort Cloud when a star passes through or near the outer shell. Its gravitational footprint sweeps across the trillion icy bodies resting there, acting like an invisible hand passing through a delicate cloud of dust. The gravitational perturbation of a passing star can send a violent shudder through the Oort Cloud, while objects deep within the inner Hills cloud remain heavily insulated and protected from the flyby. The weakly bound wanderers in the outer spherical shell experience sudden, sharp accelerations. Millions of icy mountains are abruptly knocked off their stable courses in a single cosmic instant. Some are given enough energy to be permanently ejected from the solar system altogether, condemned to wander the interstellar void as lonely orphans of the galaxy. Others are deflected into steep, highly eccentric trajectories that plunge them downward toward the inner solar system, transforming them into the long-period comets that light up our skies eons later. Through these titanic interactions, the Oort Cloud serves as a living bridge between our solar system and the rest of the Milky Way. It is a boundary layer where the local gravity of our sun bleeds directly into the vast, churning ocean of the galaxy. Every comet that falls from the sky is a physical testament to this invisible dance, carrying the scars of a galactic tide, or the distant whisper of a passing star that brushed against our cosmic home millions of years ago, reminding us that we are inextricably connected to the grander mechanics of the universe. Beneath the silent, frozen exteriors of the trillions of objects that populate the Oort Cloud lies a deeply preserved chemical record of our solar system's earliest days. Unlike the rocky asteroids that dominate the inner belt between Mars and Jupiter, which were baked dry by the fierce heat of the young sun, the inhabitants of the Oort Cloud are pristine blocks of primordial volatiles and dust. When astronomers piece together the composition of these distant wanderers, primarily through the study of long-period comets that occasionally plunge into our inner system, they find a complex, fragile matrix of materials that have remained chemically unaltered for over 4.5 billion years. Water ice forms the fundamental backbone of these icy bodies, accounting for the vast majority of their mass, but it is deeply laced with a volatile cocktail of frozen gases. Trapped within the crystalline structure of the ice are substantial quantities of carbon dioxide, methane, ammonia, carbon monoxide, and hydrogen cyanide, along with complex organic molecules. These compounds are mixed with fine silicate dust and carbonaceous grains, forming a dark, porous crust that coats the surface like soot. Because these objects have spent their entire existence in the absolute zero vacuum of the outer fringe, shielded from solar radiation and thermal stress, their internal chemistry is a literal time capsule, preserving the exact molecular ingredients that swirled within the protoplanetary disk before the planets ever took their final shape. Yet, despite the staggering number of objects inhabiting this massive realm, quantifying the total mass of the Oort Cloud remains one of modern astronomy's most difficult challenges. Because individual Oort Cloud objects are exceptionally small, dark, and located trillions of miles away, they are completely invisible to direct observation with our current technology. To estimate how much material is actually out there, scientists must rely on indirect methods, calculating the total mass required to continuously supply the observed flux of long-period comets over billions of years. Combined with sophisticated computer models of planetary migration and gravitational ejection from the early solar system, when these calculations are brought together, they yield an estimate that is both immense and surprisingly modest. Astronomers generally calculate that the combined mass of the entire Oort Cloud, spanning trillions of independent bodies, amounts to roughly 2 to 5 times the total mass of planet Earth. To put this into perspective, this mass is spread out across a spherical volume of space so colossal that it is nearly unimaginably diluted. If you were to gather every single piece of ice and dust, from the innermost edge of the hill's cloud to the outermost reaches of the spherical shell, you would have enough material to build a few medium-sized rocky planets, but that mass is instead shattered into trillions of microscopic and mountain-sized fragments, drifting in eternal isolation. This raises fascinating questions about the efficiency of our solar system's early formation and the limits of what was cast away. Over the decades, scientists have occasionally searched the outer margins for even larger hidden bodies, such as hypothetical massive brown dwarf stars or giant planets lurking far beyond Neptune. But all sky infrared surveys, like NASA's WISE mission, have effectively ruled out the presence of any stellar companions or massive gas giants in the Oort Cloud. What remains are trillions of quiet, frozen fragments, the discarded building blocks of a solar system, holding the fundamental water and organic chemistry that not only shaped our cosmic neighborhood, but may have played a critical role in seeding the oceans of our own living world. As humanity reached out into the cosmos during the latter half of the 20th century, our engineering culminated in a select few metallic emissaries designed to break free from the cradle of the inner solar system entirely. Spacecraft like Voyager 1 and 2, alongside the earlier Pioneer probes, stand as humanity's greatest physical tokens sent into the dark. Propelled by gravitational assists from the gas giants, these intrepid machines achieved escape velocity, leaving behind the warm, sunlit realm of terrestrial planets and crossing the invisible threshold of the heliopause into the true interstellar medium. They are our first ambassadors to the deep void, carrying golden records and the silent echoes of our civilization into the unknown. Yet when we measure the incredible distance they have covered against the sheer expanse of the Oort Cloud, the true scale of our cosmic isolation becomes starkly apparent. Voyager 1, traveling at a staggering speed of over 38,000 miles per hour, has been journeying away from the Sun for nearly half a century. It has crossed billions of miles of space, leaving the orbit of Neptune far in its wake. But despite this monumental trek, it has barely scratched the surface of the cosmic frontier. It is currently positioned well inside the local interstellar medium, but it has not yet reached the inner boundary of the Oort Cloud, which lies thousands of astronomical units further out into the dark. The timeline of a potential encounter between our probes and the Oort Cloud reveals the staggering gulfs of space that separate us from these outer regions. Even at their blistering speeds, it will take Voyager 1 another 300 years just to reach the inner edge of the Hills Cloud, and perhaps 30,000 years to completely traverse the outer spherical shell of the Oort Cloud. By the time these silent metal craft glide past the innermost frozen mountains of the Oort Reservoir, their nuclear power sources will have long since decayed into cold silence, their instruments dark and dormant. They will drift past these ancient icy worlds as ghost ships, moving at a glacial pace through a realm where time itself seems to stand still. This sobering reality highlights just how deeply insulated our inner solar system is from the rest of the galaxy. We have looked outward with our most powerful telescopes and sent our fastest machines toward the dark. Yet the threshold of our own stellar backyard remains virtually unreachable with our current technology. The journey to the Oort Cloud is a voyage that spans eons, reminding us that while human curiosity knows no bounds, the physical architecture of the universe demands a patience measured in epochs. Our probes are only the very first, tentative footsteps into an abyss that stretches out infinitely before us, guarding the primordial secrets of how we came to be. As we push past the outermost boundaries of the spherical Oort shell, we reach the ultimate frontier of our solar system, a silent and indistinct boundary where the Sun's gravitational dominion finally comes to an end. For nearly 100,000 astronomical units, our star has maintained a fragile, ghostly grip on trillions of frozen wanderers, keeping them tethered in slow, eternal orbits through the sheer persistence of mass. But gravity is a fading whisper at these staggering distances, growing weaker with every single mile we drift outward into the dark. Eventually, we arrive at the absolute edge of the Sun's sphere of influence, a shifting, invisible boundary known as the outer limit of the solar system, where true interstellar space begins. To understand this boundary, we must look at the invisible balance of forces that dictates the architecture of the galaxy. Every star in the Milky Way generates a gravitational well, a zone of influence where its mass dominates the motion of nearby matter. But as you travel further from a star, its gravitational pull drops off sharply, while the collective gravity of the surrounding galaxy remains steady. At the outer perimeter of the Oort Cloud, these two opposing forces reach a delicate equilibrium. The Sun's waning gravitational tug is matched and eventually overpowered by the immense ambient tidal forces of the Milky Way and the gravitational fields of passing stars. Beyond this critical threshold, an object can no longer remain bound to our solar system. It crosses the event horizon of our stellar neighborhood and enters the vast, open ocean of the interstellar medium. Here, at the edge of the Sun's dominion, the physical environment changes in profound and subtle ways. The Sun is no longer a dominant, warming presence that dictates the environment. It has dwindled to a sharp, brilliant speck of light, completely indistinguishable from the countless other stars burning brightly in the black velvet of the galaxy. The solar wind, which carves out a protective bubble called the heliosphere deep within the inner system, has long since dissipated into the ambient plasma of the galaxy. The temperature drops to the absolute minimum of deep space, hovering just fractions of a degree above absolute zero, where molecular motion slows to a crawl and the chaotic energy of stellar flares is replaced by the quiet, cosmic hum of high-energy galactic rays streaming from distant supernovae and ancient nebulae. Passing across this threshold means leaving behind the structured realm of our birth and entering the true world of the Milky Way. Objects that drift past this boundary are no longer residents of our solar system. They are liberated orphans, exposed to the raw, unshielded pressures of the interstellar wind and the gravitational currents of the galactic disk. If a passing star drifts close enough, or if a galactic tide pulls gently on the outermost fringe, the final remnants of the Oort Cloud are stripped away, scattered into the galactic current to mingle with the dust and gas of other star systems. In this grand exchange of matter, the material that once forged our planets and built our comets is returned to the greater galaxy, closing a cosmic circle that spans billions of years. As we pause here at the absolute edge of the Sun's reach, looking back across the immense, invisible expanse of the Oort Cloud toward the tiny, warm cradle of Earth, we realize the true majesty of our cosmic home. The Oort Cloud is more than just a distant graveyard of ice. It is a monument to deep time, a protective cocoon, and a threshold that bridges the gap between our local planetary system and the infinite expanse of the universe. It is where our sun's story ends, and where the greater story of the galaxy begins, waiting silently in the dark for eternity. While we often think of the Oort Cloud as a private, locked vault containing only the local debris of our own solar system's birth, reality is far more dynamic, porous, and interconnected than we once imagined. The outer perimeter of the Sun's domain is not a closed fortress, but an open, sprawling borderlands where the physical matter of the entire Milky Way constantly trades hands across vast stellar divides. Just as our Sun has cast trillions of its own icy children out into the galactic current over the last 4.5 billion years, other stars across the galaxy are doing the exact same thing, sending their own frozen orphans drifting through the dark void of interstellar space. This creates a fascinating and relatively recent realization in modern planetary science. The outer Oort Cloud may act as a cosmic collection basin, catching interstellar interlopers that originate from entirely different star systems light years away. For decades, scientists operated under the neat assumption that everything residing within our solar system shared a singular, local origin. We taught ourselves that every rock, comet, planet, and speck of dust was forged from the exact same collapsing nebula that birthed our sun. But that cozy assumption was shattered forever with the modern discovery of true interstellar objects. Rogue visitors like Oumuamua and Comet Borisov that plunged through our inner system from deep space. These strange visitors proved definitively that the space between the stars is not empty, but is actually teeming with trillions of wandering debris pieces, planetesimals, and icy shards ejected by giant planets in distant corners of the galaxy. They are the ghost ships of dead or evolving star systems, doomed to drift across the interstellar void for eternity, carrying the physical history of alien worlds into new sectors of the Milky Way. When these wandering interstellar travelers traverse our local sector of space, their paths frequently intersect with the massive, three-dimensional net of our outer Oort Cloud. To understand how frequent this encounter might be, we must look once again at the staggering physical scale of the region. Stretching outward for nearly 100,000 astronomical units in every conceivable direction, the outer Oort Cloud presents an enormous, multi-trillion-mile-wide target area. It is a sprawling, ethereal web of gravity that blankets our stellar neighborhood, acting as a giant gravitational landing net spread out across the deep cold of interstellar space. Anything passing through our local corner of the galaxy has a high probability of clipping the outer fringes of this colossal spherical shell. When an interloper from another star system approaches our solar system, it typically travels at high speeds relative to the Sun, carrying far too much kinetic energy to be easily captured. It streaks through the interstellar medium like a high-speed bullet, slicing across the galactic plane. If it passes through the inner solar system, its speed is usually so great that it merely swings around the Sun in a hyperbolic trajectory, using our star as a gravitational slingshot before exiting back out into deep space forever. However, the outer fringes of the Oort Cloud operate under a completely different set of physical rules, where the rules of capture change entirely due to the extreme weakness of the Sun's gravity and the sluggish pace of the native bodies residing there. In the outermost shell of the Oort Cloud, objects move at a glacial crawl, orbiting the distant Sun at speeds measured in mere meters per second. Because the gravitational binding energy here is so delicate, even the most subtle interactions can completely alter the fate of a passing object. As an interstellar comet or a rogue icy planetesimal sweeps through the outer edges of our Oort Cloud, it occasionally experiences a close gravitational encounter with one of our native ice mountains, or brushes gently against the collective tidal field of our Sun. While the vast majority of interstellar interlopers pass straight through unaffected due to their high velocity, a tiny fraction of them experience a slight, fortuitous deceleration, losing just enough kinetic energy to drop below the local escape velocity of the solar system. In that quiet, invisible moment, a foreign world is captured. It is gently nudged off its high-speed interstellar trajectory and trapped into a wide, highly elliptical orbit around our distant Sun, becoming a permanent, albeit extraordinarily distant, resident of our solar system. Mathematical models and galactic simulations suggest that over the course of 4.5 billion years, our Oort Cloud may have accumulated a significant hidden population of these captured interstellar objects. Trapped among the native trillions of ice mountains are foreign wanderers born around completely different stars, carrying the unique chemical signatures, isotopic ratios, and mineral secrets of alien stellar nurseries that formed light years away and eons ago. These captured interlopers look entirely indistinguishable from our own native comets at a casual glance, dark, frozen, and coated in ancient organic soot. Yet their internal molecular architecture tells a vastly different story. They are alien artifacts hidden in plain sight, resting in the deepest cryogenic vaults of our solar system, preserving the chemistry of distant parts of the Milky Way that humanity may never directly visit. This incredible reality transforms our understanding of the Oort Cloud from a stagnant storage room into a bustling, dynamic, cosmic trading post where the galaxy continuously swaps its building blocks. The exchange of matter between star systems is a two-way street operating on a grand, galactic scale. Just as our solar system captures foreign debris from passing objects, our own ejected comets are constantly being trapped by the Oort clouds of neighboring star systems as our sun drifts past them during its massive journey around the center of the galaxy. Over eons, the Milky Way stirs its ingredients together like a giant celestial cauldron, constantly sharing material, organic molecules, and prebiotic compounds across vast stellar divides. Thinking about these interstellar interlopers changes how we view our place in the cosmos. We are not isolated in some distant, untouchable corner of the universe. We are active, participating members of a vast, interconnected galactic ecosystem, holding alien secrets within our own backyard. As we reach the final chapter of our journey through the Oort Cloud, we must look beyond its current state and examine its profound connection to the existence of life itself, as well as its ultimate fate in the deep future of the cosmos. While the Oort Cloud exists today as a silent, distant cryogenic archive, resting quietly at the absolute margins of our solar system, it has not always been completely disconnected from the bustling, living world of the inner planets. 4.5 billion years ago, during the violent and chaotic infancy of our solar system, the gravitational machinery that hurled trillions of icy planetesimals out into the distant spherical shell also worked in reverse, sending a steady stream of primordial comets plunging inward toward the young, unformed terrestrial worlds. During those turbulent early epochs, particularly through periods like the late heavy bombardment, countless icy bodies originating from the outer reaches were redirected into the inner solar system, colliding with the hot, dry, and sterile surface of the early Earth. These celestial impacts were not merely destructive forces of chaos. They were the cosmic delivery systems that brought the essential ingredients for life to our nascent planet. The vast majority of the water that fills our deep oceans today, along with a rich and complex cocktail of prebiotic organic molecules, amino acids, and volatile compounds, was carried down to Earth, frozen within the cores of ancient comets hailing from the outer fringes. Without the gravitational scattering that populated the Oort Cloud and subsequently funneled those icy messengers back inward, our world might have remained a bone-dry, lifeless rock, barren and incapable of supporting the rich biological tapestry that eventually took root beneath its atmosphere. In a very literal sense, humanity and every living organism on Earth are children of the Oort Cloud. The water we drink, the organic chemistry that built our cells, and the very stability that allowed civilization to flourish are gifts from the extreme outer edge of our solar system. The comets that occasionally streak across our night skies with their brilliant, glowing tails are visiting ambassadors from our own ancient past, reminding us of the cosmic violence and migration that shaped our planetary home. They are physical proof that our existence is intimately linked to the grand, sweeping mechanics of the universe, connecting the microscopic chemistry of living cells to the massive, invisible architectures of deep space. Yet just as the Oort Cloud played a critical role in the dawn of life on Earth, it will also outlive our planet entirely, bearing witness to the final, dramatic chapters of our Sun's evolutionary life cycle. Stars are not eternal, and our Sun is no exception. Billions of years from now, the nuclear engine burning brightly in the heart of our solar system will exhaust the hydrogen fuel in its core, forcing the star to undergo a radical and violent transformation. As the core contracts and heats up, the outer layers of the Sun will swell outward to astronomical proportions, expanding into a colossal red giant that will scorch the inner terrestrial worlds, boiling away Earth's oceans and consuming everything in a fiery cataclysm. During this terrifying red giant phase, the inner solar system will be utterly obliterated or permanently sterilized, turning our warm blue cradle into a scorched, lifeless monument to a bygone era. But as the Sun expands and sheds its outer atmosphere into space, its immense distance from the outer reaches will act as a shield of salvation for the Oort Cloud. Because the trillions of icy mountains inhabiting the spherical shell are situated thousands of astronomical units away, they reside safely beyond the destructive reach of the Sun's swollen envelope. While the inner planets are swallowed by the red giant, the Oort Cloud will continue its slow, silent orbit around the dying star, largely undisturbed by the fiery death throes occurring deep within the inner system. Eventually, our Sun will exhaust its remaining nuclear fuel entirely, collapsing inward to become a dense, glowing white dwarf star, a tiny, fading ember radiating a dim, ghostly light into the surrounding void. In this twilight era of our solar system, the Oort Cloud will remain the last standing relic of our once magnificent planetary empire. The frozen bodies drifting within the outer shell will continue their eternal glacial dance in the absolute dark, preserving the chemical history of our birth in a cryogenic vault that outlives the Earth, the Sun's active lifetime, and the memory of human civilization. Yet even this monumental endurance has its limits, governed by the relentless ticking of cosmic time and the grand rotation of the Milky Way. Over hundreds of billions of years, as the white dwarf Sun slowly cools into a cold, black cinder, the Oort Cloud will gradually succumb to the external forces of the galaxy. Passing stars will drift through the local neighborhood, and the relentless gravitational tides of the Milky Way's spiral arms will tug persistently on the outer edges of the shell. One by one, over immense spans of deep time, the remaining icy bodies will be torn away from their dying star, stripped into the interstellar medium, and scattered across the galaxy. The material that once formed our solar system's protective cocoon will mingle with the vast, churning gas clouds of the interstellar medium, dissolving into the greater cosmic ocean to eventually seed the birth of new stars and new planetary systems generations down the line. In this grand and poetic finale, the Oort Cloud completes the ultimate circle of matter in the universe. It is a beginning, a guardian, a museum of deep time, and finally, a seed carrier for the future. As we close our exploration of this incredible phenomenon, we look out into the silent dark with a new understanding, realizing that the edge of our solar system is not a wall, but a doorway connecting us to the infinite, beautiful expanse of the cosmos.